My name is Paul Tchaikovsky, and this is kubectl Explain. So today, we're going to be talking about services. Pods, as we learned in the kubectl Explain pod episode, are ephemeral. They are designed to be disposable. We learned that each pod gets an IP address on the pod network. However, pods can come and go. Even with a deployment where we get that added resiliency, we do so by duplicating the pod from a template, and therefore we're never guaranteed that a given pod IP address will continue to work in the future. If you're running software in Kubernetes, you're almost always going to have a scenario where an application or a pod requires stable access to another application or pod. Without a stable IP address, we don't have a stable endpoint that we can use to ensure that access continues to function from one member to the next. This is where services come in. So a service is an abstraction that creates a consistent endpoint by defining a logical grouping of pods and a policy on how to access those pods. A service utilizes the concept of a label selector, which is a way for a client to identify a set of Kubernetes resources. This concept of a label selector is core to Kubernetes and is actually the primary grouping mechanism inside of Kubernetes. Every Kubernetes resource has a metadata field, which can contain a labels subfield. And this labels field can then be used by label selectors to group resources together. Services use label selectors to determine which pods should be accessible through the service. Effectively, a service is allowing you to decouple the ephemeral endpoints from the configuration of your application that needs to access the application inside of those ephemeral endpoints. If you have a backend application running in a pod with the label app equals backend, then your service would be configured with app equals backend as its selector, like you see here. Services are a logical grouping of Kubernetes resources, and a service in of itself simply provides this grouping and lookup function. Each service is assigned a virtual IP address called a cluster IP, and we'll use those two terms interchangeably. This is the stable endpoint to your application. However, the actual functionality of the virtual IP and the access policies are managed by service proxies and service discovery. We'll talk about service discovery quickly. kubedns is a DNS server that runs inside of your Kubernetes cluster, and it provides DNS lookups for your services. This acts as a service discovery mechanism, as each service is registered in DNS as the service name. This means that an application in the same namespace as a service named backend can be configured to connect to the host backend, and kubedns will translate that to the correct cluster IP to connect to. You can also use environment variables for service discovery, but we rarely use those these days, as environment variables are static and are created at the creation of a pod, and therefore may not actually reflect the current state of the cluster. So we almost always use kubedns as our service discovery mechanism. Now, as for service proxy, in a standard Kubernetes cluster, each node in the data plane runs a kube proxy. Kube proxy is responsible for creating the virtual IP address as well as managing access to that IP address. There are a number of different ways this can be implemented depending on the version of Kubernetes that you're running and its configuration. Regardless of the actual implementation details, the effective behavior of the kube proxy is that it creates a virtual IP on the cluster network and then creates a load balancing service on that IP address to route traffic to the pods that match the service's selector. This means that when your application attempts to connect to the backend service, the traffic will go to the virtual IP, which then sends the traffic to one of the pods being load balanced by the virtual IP. The virtual IP, or cluster IP, is only accessible inside your Kubernetes cluster, making it perfect for pod-to-pod communication. But what happens when you need to make your application accessible to external traffic? In order to provide access to the internal cluster IP, we must find a way to get foreign traffic mapped through. One of the common ways to provide such access is via network address translation, or NAT, which lets you map an IP address and a port combination to a different IP address and port combination on a different network. By changing your service type from the default cluster IP to node port, you are signaling your intention to do exactly that. So when you create a service of type node port, the service proxy still creates the cluster IP, but it also picks a free port from the ephemeral port range, and it creates a NAT rule on each node's public IP address for that port. This NAT ensures that any traffic that comes to your cluster on that port will be sent to your virtual IP and then load balanced to one of your pods. However, having to manage mappings of external IP addresses and ports of your services quickly becomes very cumbersome. To make things even simpler, if your infrastructure supports it, and it probably does, you can instead set your service to type load balancer. A service of type load balancer still creates both a cluster IP and a node port. However, it also signals to the Cloud Controller Manager that it should configure a load balancer on your cloud's infrastructure to load balance for the external IP address of each of your nodes on the node port's assigned port. Likely, within a few minutes, your cloud will have created a load balancer with a static IP address that balances the traffic across your Kubernetes nodes. Usually, your load balancer will be hosted on a standard TCP port, such as 80 or 443, definable by you, and thus you have a stable endpoint to which you can assign a DNS host record and provide a friendly named endpoint for your application. So services, like all things in Kubernetes, we start with a fragile concept, such as a pod IP address, and then we layer on extra functionality until we have a suitable stable interface, such as a cluster IP or a load balancer. Kubernetes has even more complex networking and service discovery through things like ingress controllers and service meshes, but we'll talk about those in a future episode.